we can on this practice test from 2014. Okay, so we only have 26 questions down here. You got them done in one period. But let's talk about why each of these was right, which ones were wrong. There were some that, as I looked over your answers, were clearly easy, like this first one. The first one was a very easy problem. Let's take a look at it. It's all that garbage that they write in there, and it's like a paragraph's worth of nonsense about, kinetics experiment is set up to collect the blah, 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 blah. I mean, sometimes you kind of like just skim through that stuff for speed-wise and just see what the question's asking you. Other times you have to read it very, very carefully. In this case, when you go to read the answers, when you go to read the actual answers, it says, which of these is going to make this reaction go faster? Now, do any of these make sense? Most of you realize that A does not make sense. Decreasing the volume, or B, decreasing the concentration of the ethanoic acid, is not going to make the reaction go faster, right? It's going to make it go slower. Decreasing the temperature, again, not going to make the reaction go faster. It's going to make it go slower. The only one that makes sense there is decreasing the particle size. In other words, crushing it, increasing the surface area. We talked about that from Chem 1. We talked about that in kinetics. Almost everybody got that one right. Okay? All right, and there will be some as easy as that on the test. All right, now let's get to number 2. We don't want to spend time on things that are really easy. Here you got a 100-gram sample of metal, and it says it's heated to 100 degrees. This is exactly what we did in multiple places in the thermodynamics chapter. We did it to calculate specific heat of like 4 different metals. We put them in hot metal and cold water, measured the final temperature. We did it for Hess's law. So we did it in like a couple of different labs with the coffee cups. So here's the question. Let's see what makes sense down here. Obviously, there's a temperature change, and it tells you what happens, tells you what the final temperature is. Now, why don't these make sense? The first one says the metal temperature changed more than the water temperature did. This is correct. The metal temperature did change more than the water temperature did. Therefore, the metal lost more thermal energy than the water gained. Now, that's not correct, okay? Right? So you should have eliminated that one because that would be a violation of the first law of thermodynamics, correct? Okay? The second one, the metal temperature changed more than the water temperature did, but the metal lost the same amount of energy as the water gained. That is the definition of the first law of thermodynamics, and absolutely true. Why did the temperature of the mass or the metal not change as much? Well, there wasn't as much metal there, and his specific heat probably is different than water as well, so that will make a difference as well. So the correct answer should have been B. The other guys don't make sense because of the heat capacity it talks about of the metal. Well, that would be wrong. Actually, the heat capacity is lower, it says, for C. And, of course, D would be a total violation of the first law of thermodynamics. It says the final temperature is less than the average starting temperature. Therefore, the total energy of the metal and water decreased. That's not possible. The total energy has to stay the same. All right, if that's why you're able to do these calculations, to calculate the final temperature. All right, because the amount of energy lost has to equal the amount of energy gained. Okay, so that's a thinking question about thermodynamics. You didn't have to do any calculations. By the way, you'll notice there's very few calculations to do in these. All right. Now, 3 is a good example of what your test might look like. You look at 3, and it's very easy to do this dumb mistake. I got 2 things here. There's 2 more over on the other page, right? Don't forget to look for all of the things. Sometimes you may have A, B, C, D, E, and you might miss one on a different page, okay? Now, let's see why the first one doesn't make sense. First one doesn't make any sense because if you add them up, there are too few of what must be hydrogen molecules on the left side than there are on the right side. But there's a bigger reason why A and B are both wrong. Why are A and B both wrong?
Because hydrogen and oxygen gas are made up of 2 molecules.
Exactly. They're both diatomic. So I'm down to C and D. Of C and D, which of those makes sense? Well, again, we have a violation of the law of conservation of matter and energy. All right. If I look at C, I have exactly the same number of oxygen molecules. Not molecules, but oxygen atoms on the left as I have on the right. In other words, I have twice as many hydrogen molecules as I have of oxygen. That makes sense, because water is H2O. In D, if you count them up, just physically count these guys up, you'll find you have way too many dark-colored ones, that's the oxygen ones, than you have on the other side. So that's a violation of the law of conservation of matter and energy. Can't create or destroy matter and energy. By the way, I'm trying to give you, as I'm doing these, if any of these were in form of a short answer free response question, and they ask you to explain it, notice what I'm doing. violation of the first law of thermodynamics, violation of law of conservation of matter and energy, violation of Hess's law of heat summation. This is what you'll want to do to get full credit when you're explaining your answer. You're not going to want to just say, well, there's too many atoms on this side than on the other side. That's correct. I mean, you'll probably get points for saying that, but you're probably not going to get full credit unless you use the exact terminology. All right. I got to tell you, these are where two of my three mistakes came when I did this between 4 and 7. Okay? And again, it's another example of what I said the other day. What I hate about these exams is that they'll give you one thing in a multiple choice format. There's only 60 questions, for crying out loud. And then they'll ask 5 questions about that one thing, and if you misinterpret it, or if it's one of the things that we just didn't cover very well, or covered in Chem 1 and don't remember, you're screwed. I mean, you're basically going to get a lot of points off for one concept. And that doesn't seem fair to me. All right? And this is a great example of that. And also it's a great example of what I think is a really, really difficult question. I looked back at it just today, because the first day I really had no clue why I got this wrong. I really didn't know what they wanted here. But here, this is my best guess as to what the correct answer for number 4 should have been. All right? It gives you this plot up here. Whoops, there it is. It gives you this graph up here. And it asks you some questions. It has Q, R, S, T. Right? And like, I don't know exactly where they are, but basically Q here, R, S, T there, and then U up here. Okay? Now, let's look at the first question, because almost no one got this right. And if you got it right, you probably guessed. Okay? Because I guessed. All right? And I'll tell you what. It doesn't, there are two, it seems to me, here's my logic as to why. Which one of those 4 can I eliminate at point R? What obviously can't be the highest concentration?
OH.
Right, OH. Everybody knows that. The pH is below 7, so no one's going to put down D. If you put down D, I don't know what you were thinking. All right? There's no reason to put down D. Now, A, B, and C all seem to make sense. And I'll tell you right now what I should have chosen, and it should have made sense to me, even though I wasn't thinking. I'll tell you what the logic of it is now. My logic should have been this. The concentration of H3O and A pretty much have to be the same, right? Because for every time HA breaks up, you're making one A minus and one H3O, right? So I should have eliminated those knowing that those two had to be the same and HA had to be the correct answer. But here's my problem. I didn't think. I didn't look at this and realize that HA had to have been a weak acid.
Sophomores with last names beginning with the letters
All right.
H through K.
And that's the key. I know you. So a lot of you are thinking to yourself, like, "Oh, I got that right. I knew what I was doing." No, you didn't. Not unless you were thinking about HA being a weak acid. Because if HA is a strong acid and you do this titration, the concentration of HA at that point is not the greatest. H3O would be greater, right? Because what does a strong acid do in solution? Breaks up completely, right? So that's the whole point. The whole point of this is realizing that HA must be a weak acid. And by the way I should have known that is that the equivalence point is actually above 7, isn't it? Okay? So I missed that. And if you miss something like that, that's it. I mean, it's going to hurt you, not just for that one, but usually for other ones that follow. Well, let's see what. So the correct answer was A, HA. That was the correct answer for that guy. Now, that doesn't hurt you for 5. Again, 5 is again a process of elimination. It's asking you what concentration of the particles, what must this look like in this container at U? And why is this a process of elimination? Because if I'm at U, I'm in a base. There are no OH ions in A, there are no OH ions in C, and there are no OH ions in D. The only one that has OH ions is B. That had to have been the correct answer. Does everybody see that one? That makes sense. Okay. And here's another one. This is one of those which this is the other one I got wrong on this. I got 2 wrong out of this, and this was the other one. At which point on the titration curve is A minus closest to to twice that of HA? Honestly, there is a way. We did the Henderson-Hasselbalch equation. You can calculate pH and concentrations, and half the equivalence point is at S. All right. So basically, if you remembered all that, you should have realized that the correct answer was CT, where you would have had more. Yeah.
Oh, wait, never mind.
Where basically A would have been greater than HA. All right. But I never taught that to you. I never taught you to interpret the graph in that way, shape, or form. We did lots of calculations we graphed this, we did this titration, but so I would not expect that most of you, if you got that right, it was totally a guess again. I mean, there were obvious wrong answers. It couldn't be you, right? So, you know, there are obvious wrong answers, but again, you would have had a hard time getting that one right. All right, let's get away from that one finally, I think. Or no, there's still one more question. All right, oh my God, this is one of my favorite horrible questions again. Because it really, it's not even a question of do you understand the concept. All right, so I kind of want to go off on a tangent here and explain why I hate this question so much. Here would have been a good question. A good question would have been, student carries out the titration, calculate the molarity of the acid at, you know, what's the final answer? What's the correct answer? And of course, you had to do what? You had to do NAVA equals NBVB. Right? All right, that would have been fine. And of course, the numbers are easy enough that you could do them in your head. If you want to calculate the concentration of Na, if you reread that question, you'll see that Na equals, you know, NBVB over VA. You're given the normality of the base. It tells you the normality of the base, I believe, was 0.1. Is that right? Look back at the question here. I have it somewhere here. It's like 2 pages. And that's the other. You notice also how annoying this is. Flipping back, really 2 pages, 2 full pages back. Yeah, the concentration was 0.1. It tells you in the problem, molar. The volume of the base at the equivalence point, the volume of the base, this tells you this is the NaOH, was 40. All right, over the volume of the acid. How much acid did it say it had in that beaker or Erlenmeyer flask? It said it had 50 milliliters, right? Okay. Now, when you do that, 0.1 times 40 over 50, basically, what do you get? You could probably do that in your head. You should be able to do that in your head. You get 0.08. Is that correct? 0.08. All right. If they had just asked that, I have no problem with that, but they didn't. They had to go on one step further just to make sure now, to answer that question, in my opinion, shows a great knowledge of the concept. You had to be able to use this graph to realize that the endpoint indicated the point where the volumes were the same. You had to know how to use this equation and then solve for a missing variable and therefore predict the concentration of the unknown acid. All right? And that would clearly show it. But no, they had to go one step further. They had to say, you know, this person redoes this experiment now. And the indicator changes color a little late because it doesn't change right at the endpoint. So what would the concentration be? You got to now think to yourself, was it going to be more or less? And I'm thinking about this. Of course, you spend enough time doing this problem. You only get like 1.5 minutes per problem, right? You spend enough time doing this problem. Now I got to start thinking to myself, and this happens again in the thermal question later. Okay, so what happens now? And I have to think to myself, well, if I make the endpoint a little bit later, what's that going to do to the volume of this base? It's going to make it a little bit higher, 41 or 42, right? It'll have been shifted over a little bit. So I look, that makes the volume of the base slightly larger. What will it do to the size? In a numerator, it becomes bigger. What will it do to the size of the normality of the acid? Make it slightly larger. Therefore, your answer is slightly more than 0.08, which is B. But there's no reason to throw that in there. There's no reason to throw that in there. If you chose A, how many chose A and got it wrong? I don't know. Anybody here choose A? Nobody? Wow, that's amazing. Because if you chose A, it shows that you knew how to do the calculation, you got 0.08. Well, it doesn't show that. You might have just guessed A. And then you just did it backwards in your head about which one would be larger or small. But that's just dumb. It doesn't really show you that you understand. You obviously understood the concept to get 0.08. You clearly understood it. And now they throw that last curveball in there at you, which I just don't understand why they have to do that. There's really no reason for it. Anyway. All right, this next question's they are tough. I got to tell you, and another one of those where you really got to think. The first one's easy. All right, the average kinetic energy of the gas molecules, number 8, has to be D, the same in all 3 containers because temperature measures average kinetic energy. Okay, so that's really the answer there. All right, now the next one though is so hard, and they made it so close to being the answer. You're gonna hate this one. Anybody who got this, unless you thought this through the way I'm thinking it through, you probably guessed that and got it right. You probably just guessed. All right. So if you put down B as the correct answer, here's what you had to go through with in your head to get this correct answer. You had to realize that D equals M over V. Right? Okay. Density equals mass times volume, or mass over volume. Okay. Now, according to that, if we look at who's got the largest molar mass. Okay? It's who? Who has the largest molar mass in that chart? Butane. So butane wins because butane has he has 2 times the molar mass of his nearest competitor, which was, I believe, ethane, correct? So he has twice as big. But here's the kicker. Ethane may still win this battle. You say, why? Well, because ethane's pressure, look at that chart again. Ethane's pressure is twice that of butane's. So you have to realize that PV equals nRT. So V equals nRT over P. All these being equal, ethane's pressure is double, which would make V smaller, which would make density greater because it's in the denominator. But how much smaller is it? Is it an obvious amount smaller or bigger? No. It's almost exactly double. They did this to you. They made it almost exactly, they made that one exactly double and the other one almost exactly double. It's 38 for the molar mass and, 30 for the molar mass and 58 for the other molar mass. So, oh my God, I must have plugged it into my head like 15 times before I realized which one's going to win out. And if you do this, you realize, I need my glasses to read my own handwriting here, ethane, according to this, ethane should win. According to the other one, butane should win. But butane isn't quite exactly double. It's a little bit less. It's 58, So the actual winner is going to be B, which is ethane. Because it's exactly double. It's more than, the other one was almost double, but not quite double. Now again, there's no reason to do this. This is a stupid, horrible, terrible question. And they do it again with that K plus 1/2 Cl2. You don't realize this, but they made the mass of potassium almost exactly the molar mass, almost exactly 1/2 of chlorine, which is a real pain in the neck because 1/2 is also a coefficient, and you got to find the limiting reactant. There's no reason to do this. If you understand the concept of limiting reactant, you don't have to make the numbers so close. Because this is like 35.5 times 2 is like 71. This guy's 39 times 2, which is like 78. They're almost exactly double, all right, which again makes the numbers really, really tough to do when you get to that problem. I just don't understand who makes these things up and why they feel they have to do this. I got this one right, but I had to think about it for more than a minute and a half. And I think anyone who's not really, really, you could understand chemistry, but not be really fast with the math, anybody would take at least 3 or 4 minutes to have to figure this all out. First, you'd have to realize I need to use these 2 equations. Then you'd have to rearrange them, figure out how they're being affected, and then realize how close they are, which guy actually wins out. And it's so hard to keep that straight in your head. All right, but anyway, that is the correct answer, and that's how you do it. How many got that one right? Did you think like that, or did you just guess? My guess is you just guessed. All right, it was a strictly a guess because no one really considered the fact that how pressure would have affected the volume and therefore increasing the denominator, making it small. It's just amazing.
I just assumed the more pressure there was, the more dense it would be.
But you completely ignored the molar mass, and that you're not lucky that the molar mass didn't win out. If the molar mass had been different by 2, 3 or more grams more, then you would have won exactly wrong. So it's just sheer luck, and that's just I hate this. All right, let's get back to the number 10. Number 10 is not that bad. It's going to condense. The guy who's going to condense first is going to be the guy with the larger molar mass. The guy is heavier, right? And so that would be C, butane. He's the biggest one. All right, let's turn the page. This guy, I kind of like this question. These couple of questions about him. This is not bad. All right, the first one says, why would I get an increase in pressure when this reaction's over? You have to realize we've got PCl5. This is something we talked about in equilibrium. PCl5 is going to, what is it going to? PCl3 and Cl2. PCl3 and Cl2. Now, all these guys are gases, I believe. Is that correct? Are they all gases? Yeah. All right. Remember what we talked about. Gases pretty much act as points, according to the ideal gas law. So the more gases I have, the more the pressure is going to basically be that much increase. And I can also determine, it's going to favor which side. Volume and pressure changes are going to favor which side, okay, based on that. So the question is, Which of the following is most likely the reason for the increase in pressure? When you're done with this equation, when this guy's at equilibrium, it started at 1.0 atmospheres. It ends at 1.40 atmospheres. Why? Because there are more molecules on that side, right? And more molecules bang into the sides of the containers more. Your correct answer was C. All right, an increase in the number of molecules. Everybody got that one? That one you should have been able to figure out. And also, number 12 is a classic example of how I've spent, again, probably not the easiest way to explain it, but let's read the question. As the reaction progresses towards equilibrium. So, remember doing this? I even used different colors. I said, in the beginning, you only have a forward direction and there's no reverse direction. You know, and when you first put the stuff in the equation. Over time, what happens? The forward direction slows down, right, over time, and the reverse direction increases. Until they're both what? Equal, right? So we remember doing that. I used the colors. We talked about it. We did calculations with it. Well, which one of those answers actually says that's what happens? C. The forward direction will decrease until it becomes a constant non-zero rate at equilibrium. Now, again, that's just an ugly way of saying, you know, it decreases until it's the same as the other rate. All right? All right. Remember Stosh and Stan walking back and forth carrying bricks across the road. Okay? They're working at the same rate. That's what happens at the end. They're still walking back and forth, but they're not actually making any change. All right, let's look at 13. If the decomposition reaction were to go to completion, the total pressure, and this is a common sense kind of thing. If it goes to completion, I got twice as many molecules on that side, don't I? So if the pressure started at 1 atmosphere, what should it end at? 2. Okay? All right, that makes sense. All right, now let's look at 14. Which of the following statements about Kp is correct? Now, this is a good, again, common, like a theoretical question. It actually ended at 1.4. We just said in the previous problem it should have gone to 2.0 if it went to completion. Did it even go halfway to completion then? Did it go halfway even? No, it didn't, right? So if it didn't go halfway to completion, what do we know K is? Kp, K, after all, ratios of the forward to the reverse rates, right? So what do I know? K has to be smaller than 1, right? Less than 1, which I guess the answer is B on that one, correct? Okay, you have to remember that about equilibrium problems. You are definitely going to see equilibrium problems where you have to understand the value of what K means. Remember, really, really small Ks, Ks like times 10 to the negative 14th. Where do we see them? We saw them in weak acids. Why? Because weak acids didn't break up in solution very much, to much extent. Okay? Large Ks mean it goes almost entirely to completion. You know, K of 1,000 means it's going to go almost completely to the product side. All right, what's next? The only one of these graphs that would work, all right, you have to realize something. When you inject a product, the reverse rate is going to increase immediately. But then over time, the forward rate's going to pick up to try to balance that out. So the only two that are logical are B and C. All right, but of the two, you have to realize it's never going to get back below where, if I added a product, aren't I going to favor the reverse reaction? So therefore, the reverse should have been higher at the very end where it levels back out again. 16? Yeah, here's that one again. I just love this guy. Yeah, they basically, when you get to a question a little bit later, you're going to see how I just don't know why they feel they have to do this. That equation is a legitimate equation. It's a molar enthalpy of formation equation, which we did many of. So let's take a look at that equation. K plus Cl2 yields, and that's 1/2 Cl2 yields KCl. Right? Now, we actually did molar enthalpy of formation equations, and he's a solid, gas, and solid. So solid here, gas here, solid here. Okay? We did a lot of these. All right, let's take a look at the first one. First question. How much heat is released or absorbed when 0.05 moles of chlorine is formed from KCl? Well, it tells you the delta H is negative 437 kilojoules per mole. Now, it wants to know how much you're going to get if I were to make this from that. So the first thing you realize is going to be a positive. You're going to eliminate immediately A and B. Because it says A and B says that much energy is released. That will be a negative value, correct? So if you put down A and B, you weren't thinking. All right? C and D are your two choices, and here's where you had to think about your concentrations. Now, it tells you have 0.05 moles of it, correct? If it were exactly 0.5 moles, that's a half a mole, and your answer would have been positive 437, correct? If I have got 0.05 moles, what am I going to do to the decimal place? One space over, so it'd be positive 43.7, which was the correct answer, which was C. All right. Now, what would remain? This is the other one I was telling you. I was hinting about. I'm going to go off on this packet again. Okay. What does it do here? This is a limiting reactant problem. And I have no problem with limiting reactant problems. I know you're going to see limiting reactant problems. But did they have to say it this way? Let's read this question. What remains in the reaction vessel after equal masses of K and Cl2, equal masses, not equal moles, have reacted until either one or both of the reactants have been completely consumed? Well, you've got to figure out who is your limiting reactant. So let's see if we can do that. I have equal masses of both of these guys, which, if they said equal moles, it'd make the problem a lot easier. Okay? But they didn't. So I'm going to choose a number. Here's my head. You may have thought of a better way to do this. I don't know. My head, I'm going to choose about 40 because that's about the mass of potassium. Okay? 40 grams of potassium, grams at the bottom, moles at the top will give me 1.0 moles and make my numbers easy. And remember what I said about limiting reactants? Just divide by the coefficient, correct? So 1 divided by 1, that'll be easy. But here's why it gets confusing. If I use 40, I remember it said equal masses. 40 grams of Cl2, it's almost exactly half, isn't it? But not quite. All right, 40 grams at the bottom, moles at the top. 1 mole contains, for Cl2, it's going to be about 71. It's going to be a little bit less than that, right? If it was 80, it would be half, right? So it's not, so if it was 80, it would be half. It was smaller than that, so it's going to be a little bit more than half, right? Right? Is that right? See, again, I can't even think about this. Your answer is going to be about 0.6, okay? A little bit more than half, if I were to do this in my head. Okay? 0.6 divided by 0.5 is slightly, this guy's answer is 1. It's slightly greater than 1, maybe 1.1. So you figured out you've got more chlorine than you have potassium. You still have to use your head. That means potassium is the limiting reactant. Potassium is the limiting reactant in this case. All right? So he is all used up, correct? What would be left in the container? You might think to yourself, well, there'll be chlorine left. No. You have to also remember the reaction went to completion. So you'd have also KCl. Both chlorine and KCl will be in that container. That's the answer, C. Again, is there an easier way to ask a limiting reactant problem? I would think there's a lot easier way to ask the limiting reactant problem where you're not going to get numbers that come out to be almost exactly the same. But I didn't write the test. I think that's a little stupid, but what are you going to do? Now, let's take a look at B. This is a thinking problem here. 18B is the answer. Let me tell you why. If we look back at that chart, look back at the chart on this page, page 127. It wants to know which of these reactions indicate an exothermic process. In other words, energy would be released. Let's look at the first one for V. Solid potassium going to gaseous potassium. Is that going to be endothermic or exothermic? Think about it. Endo. Yeah, it's going to take energy to boil solid potassium. Okay? How about taking gaseous K and adding, removing an electron from it? Removing an electron. What's going to happen? It's going to take energy again, right? So that's not going to be exothermic. Taking a chlorine molecule and splitting it up. We know that takes energy. So those three are all endothermic. Adding an electron to almost anybody, but certainly adding an electron to chlorine is going to give off energy. It's going to be happy with that. It's going to want that. So that's going to be an exothermic reaction. And then K plus and KCl forming KCl solid is going to also be a spontaneous reaction. So both of those are Y and Z are the correct answers. All right, where they would actually be exothermic. This is. I'm glad we're almost running out of time. I have 2 minutes. This is the last one I'll do. I wanted to get to this one anyway. Number 19. It says, why is it correct? I bet a lot of people got this one wrong, thinking it's driven by both enthalpy and entropy changes. I bet a lot of people thought that. Everybody look up here. You have to keep in mind, that delta G equals delta H minus T delta S. Remember? So, a negative delta H favors spontaneity, I mean energy decreasing or exothermic, and a positive delta S. So, why is it only enthalpy that drives that equation? Look at the equation. You're going from a guy that's got a gas and two particles to becoming something that's a solid. Do you think that's a favorable entropy change?
No.
No, entropy wants to get more random. You know, going from a solid or a liquid to a gas, that would be a favorable entropy change. This is only favorable versus the enthalpy. It is confusingly worded. I wouldn't have worded it exactly that way. All right, entropy is absolutely involved. It's just not favoring it. Entropy is not favoring your spontaneous reaction. Okay, pass those back.